Hey guys, welcome to video 3. In video 2, we were able to create a beautiful plot of the efficient frontier, the global minimum variance portfolio, the equally weighted portfolio, and the market portfolio. And while the MVP is useful in constructing the efficient frontier, it has little practical significance beyond dealing with an individual that's infinitely risk averse, which really never happens. So today we're going to build on the MVP and apply additional return and risk constraints to our portfolio. So the first of the two portfolios we're going to build is a minimum variance portfolio subject to the portfolio's return equaling the average annual excess return on the market that we calculated. This is our MUM variable. To do this, we return to the PowerPoint in our optimization program. So we're now dealing with an additional constraint where the transposed vector of weights multiplied by our portfolio's return is equal to the excess return on the market from our sample period, or 19.27, our MUM variable. So we set up the Lagrangian function, and with an additional constraint now represented by this lambda 2. And we take the first order conditions with respect to W, lambda 1, and lambda 2, and you can see they've been populated here. You can now see that W star can be solved out for by moving the lambdas over to the other side and multiplying by the inverse of the covariance matrix. And we notice that there's only two unknowns now, which is lambda 1 and lambda 2, because we know the inverse of the covariance matrix. We know the vector of ones, which is represented by I, and we know the estimated return from the portfolio, which is our mu variable. So we can now reinsert W star into the second and third first order conditions to solve for lambda. Once we expand the expressions to include W star, we notice that the A, B, and C variables we've been calculating are all represented here. So we can then represent this as a linear system with matrix equation and solve for the lambdas. We'll then reinsert the lambdas into our first order condition to get the optimal weights, and then we'll calculate the return and standard deviation from there. So we now return to Python to code our new portfolios. Okay, we're back in Python and are now just representing our linear systems as the matrix equation AX equals B. So the first thing we need to do is form our 2x2 matrix. So we'll set the variable A equal to np.matrix to form our matrix. Parentheses, the first bracket or the first two rows will be AA, BB, and the second row of the matrix is going to be BB and CC. So the next thing we need to do is invert this matrix. So we'll denote this variable A inverse, and we'll use the np.linearalgebra.inverse function, and then we'll just throw our matrix A in there. And the last thing we need to do is calculate our B column vector. So we'll set the variable B equal to np.matrix. And these are our constraints. So the first constraint is our portfolio weights equals 1. And the second constraint is that our portfolio return equals the excess return on the market, or our mu-m variable. Before we calculate the optimal vector of weights, we need to calculate the lambdas. So we'll denote the variable lambs equal to the A, our inverse covariance matrix multiplied times B. And again, this is just solving the matrix equation AX equals B for the unknown lambdas here. So we can then reinsert those into our W star from the first order condition in the PowerPoint. We'll denote the variable W1 is equal to the inverse of the covariance matrix multiplied by the dot product of the transposed product of our first lambda, again, subsetting the first lambda from our zero row, or our first row, based on Python notation, multiplied by a vector of ones. And then we're going to add this to the inverted covariance matrix multiplied by the transposed product of the second lambda, denoted by the one row, multiplied by the np.array times our vector of returns. And that will allow the calculation for our optimal weights that you can see here. We now have the necessary information to calculate our portfolio statistics. So we'll start with the mean, and we're just taking the dot product between the transposed vector of weights by our mu vector, which is the average annual return of the 47 industries. And we wanted that to be correctly constrained to our excess return on the market. So this portfolio returned 19.27, and the excess return on the market is our mu-m variable. And you can see that this optimization process has correctly constrained our portfolio's return to that of the excess return on the market. To calculate the standard deviation, we first need to convert the matrix into a numpy array. So we use the np array function, and then we're just taking the dot product of the transposed vector of weights by the covariance matrix by the vector of weights. And this is just a known formula to calculate the standard deviation of a portfolio. And then we need to change the data type to a float variable, because if we don't and we try to take the square root, it's going to say the data type needs to be an integer. So if we look at the standard deviation here, we can see that the standard deviation is slightly higher than the minimum variance portfolio, but we get a significantly higher return at 19.2. The final thing we need to do is add this minimum variance portfolio subject to 2 constraints to our existing plot. So all I've done is gone ahead and copied this plot code down, and we just need to manipulate it a bit. So we're going to add the standard deviation of this portfolio, and then we'll add the return of the portfolio, which is MU1. And then we also want to add text. So we'll copy this code and just manipulate it a bit by changing the variable names. So we'll change it to sig1, mu1, and we'll call this portfolio M1. And if we execute this, we can see the portfolio M1 has been added and has significantly higher return for marginally more risk. But this frontier isn't necessarily practically realistic, and we'll get into those issues later. But for now, this is the end of this video. And in the next video, we'll look to add another minimum variance portfolio subject to an additional constraint that the beta of the portfolio is equal to 1. I hope to see you guys there. Thanks for stopping by.